we're in Geometry Pace 1116. It's our number 8. The start of it is review. It reviews ratios and proportions. And I do, in fact, hope that you find this pace to be a lot of review with just a little bit of building. Because a ratio and a proportion can also be called a fraction.
Yay.
Yeah, fractions. So we're mainly going to be focusing on fractions, fractions with exponents, like negative exponents. What does that mean? And then also square roots. Now, how do square roots come into play or factor into play when we're talking about exponents? Could there be an exponent that represents the same thing as a square root? And could that exponent be a fraction? We'll find out on this journey. But for now, it's just pages 1 through 5. Pages 1 through 5 reminds us of ratios. And it's helpful to know cooking ratios if you're trying to convert, ounces to something else that's cooking related. I haven't done a lot of cooking conversions recently. But maybe you can't get to your phone because your hands are covered in floury goop and you can't hit it. And maybe, you forgot to activate your Hey Siri voice thing or whatever. And maybe you don't have an Alexa. Those are kind of things that most people would do. I get it. You're like, hey, convert this for me. But you need to just do it in a pinch. How would you be able to do that? Well, the first step is even easier than that. It just says write the ratio of the first number to the second number. And it even tells you what they're really getting at is write it as a fraction. So how would you write 5, 90 as a fraction? Indeed, it's 5 over 90, right? So we get what we're doing on this page?
No, I think it was confused.
Are we confused by a ratio as a fraction? 5 to 90 is 5 over 90. He read the whole directions. I didn't even say that part yet.
What?
Now it does say in lowest terms. So you would have to ask yourself, does 5 go into 90?
Does 9 go to 13?
Does 5 go into 90?
No. Yes. Wait, yes, it does.
Well, 5 goes into 9 one time with what left over? 4. So you'd have 40 left over. And so what is your actual final fraction in that case? 5 over 90 simplifies down to 1 over 18. Yeah. So that's what page 2 is all about. You're just quickly writing ratios. And you're writing it as a fraction. And then some reduction. Page number 3, the directions just say fill in the blank. We get to look together already. We're still in single-digit page numbers and we're already doing word problems. I mean, can it get any better than this? Was that a sigh I heard from the back of the room? No, it can't get any better than this. We're already on word problems and it's only page 3. The example says, find the measures of 2 complementary angles whose measures are in the ratio of, and what does that say?
4 or 5.
Are we looking at the example together? 2 over 7?
7.
Are you giving the answer? Where'd you get 4 over 5?
He went to 18.
Oh, yes.
Oh, yeah, it's the same one.
The reminder there is 2 complementary angles add up to a sum of how many degrees? 90 degrees. 2 supplementary angles add up to a sum of 180. So it gives you those, and it gives you this nice little ratio and how you can think about, does the ratio, though, make sense? How would this 2x plus 7x equals 90 how would we ever come up with such an equation just given that my ratio is 2/7? Does that make sense? Does it make sense?
Mm-hmm.
Well, if I put x in my ratio, those would cancel out, so I would see how I would have a 2/7. So 2x and 7x. I can combine these and finish my solution. So 2 plus 7 gives me what? 9x equals 90, so x comes out to 10. You see that there in your instructions. Then you check it by putting 10 back in for x, and you find that it works. So let's skip 19 to 19, because it's more exciting to deal with actual things that you might do. You might actually need to cut 2 pieces of wood, 2 wooden boards. You're building something. I don't know. What are you building? Well, it's up to you. You know what you're building. You have a board that is 50 centimeters long. Now, is that really long or not so long? 50 centimeters. That's not so long. It's cut into 2 pieces whose lengths have a ratio of 3:7. Now, this would be a very special kind of building project when someone's communicating to you, I need a ratio of 3:7.
I'd look at them and I'd be like, I'd have concerns.
But you would know how to do it according to this. What is the length of each piece? You got this 50 centimeter board. So I suppose 50 is going to go here in place of this 90, because that's our total. And my ratio is 3:7. So that means I have 3x plus 7x equals 50. So this one here is problem number 19. This one was the example. See how I got this equation from what they gave you? What's my next step? I combine these to get 10x equals 50. And divide by 10 and get x is equal to 5. Am I done? No, I'm not done, because I need to know what the length of each board is. So the 3x board is 3 times 5, and the 7 is 7 times 5. 3 times 5 gives me 15, but what's 7 times 5? Can you do that without a calculator? Of course you can. What's 7 times 5? You know your times tables. Does, oh, I put the plus there, really. If I'm adding, it should be there. Do these two add up to 50? Indeed they do. And just a little check.
Do we have to check?
So what are the lengths of my board? If I'm truly answering the question, it's 15 centimeters and 35 centimeters. That's the length of my board. Number 20. I'm going to have to do a little erasing to make room for 20. What do you think the equation is going to be? Well, what's your ratio? Number 20. The measure of 2 supplementary angles. What do those add up to? Well, they gave you the answer in the hint, but you would know it was 180 even without the hint, right? Yeah. And my ratio is 1 to 5. So I have a 1 to 5 ratio. It can be also written like this, but we also learned it can be written like this. So I have my 1x, or x, plus 5x. That has to equal 180. I combine these to get 6x equals 180. And I know that if I divide 180 by 6, I'm left with, well, you know the answer there. Write it down. And then you get to multiply that answer by these two. And you'll find that 30 plus 150 does add up to 180. Those are your two angles. Any questions about those? No questions. Nice. Proportions and properties of proportions. That's a lot of P's there in there. It makes me think of that Mr. Popper's Penguins, his secretary who spoke only using words that start with P. You haven't seen Mr. Popper's Penguins? Really? Old Jim Carrey movie. So that's his name, Mr. Popper. And he has a secretary who only speaks in words that start with P. So, proportions and properties of proportions makes me think of that, because they only start with P. A proportion is an equation stating that two ratios are what? There's no P word here. It's an E word. Equal. It's written in the form of A. Now this is really important to note. We're not just spouting out letters here. This is something you will be learning and utilizing as we do this together, these proportions and solving for them. So A over B, let's get rid of this because that was problem 20 from the other section. Now we're looking at this new thing. A over B, that's supposed to be an A, equals C over D. If this is a proportion, then the equal sign is appropriate because they are going to be equal. One may need to be reduced in order to equal the other, but they are equivalent. A proportion is an equation that states that two ratios are equal. They can be set to equal each other. Of course, B and D can't be zero because you can't have a zero in your denominator. And then it gives us some examples. You can see those examples. 12 over 36 is equal to 1 over 3. And the others as well. Now this is an important statement. You're going to want to start marking, a little highlighting. Each of the positions in this proportion, A over B equals C over D, it says is numbered because each is technically a singular word, so each is numbered. The first term is A, B. The second term, C, B. The first term is A, second term is B, third term C, fourth term is D. Every time I read this, it messes me up because the first term is A, B is the second term, C is the third, and D is the fourth. They switched the order in which they wrote it every time. Gets me every time. So here's a good way to look at it. So first term is A. What's my fourth term?
D.
All over here to D, fourth term. What's my second term? B was second, and my third term is C. He goes on to say, in any proportion, the first and fourth terms, the ones I've written with red, are called the, what's that next word? The extremes. And the second and third terms are called the means. So these blue ones, C and D, are means. You can think of like means. Here, means is the term for that, and then extremes. These ones are the extremes, A and D. So I could even write it with red on top. And then, I don't know if this blue is going to hold out much longer, but let's try the blue. Look at that. Turned it into blue. Like magic. Proportions are also written in these other forms that we've learned, where you can have your dots. Whoops, I need that marker. You can have your dots. So it tells you there 4 to 9 equals 12 to 27. They're pulling that from the first example. So 4 to 9 would be like A to B equals C to D. But we already knew that. We know that you can rewrite a ratio like this already. In this case, the extremes appear on the outside and the means are on the inside. That's when you write it like with, let's just use their example so we have a solid thing to look at. So 4 over 9 equals 12 over 27. If I wrote it like this, 4 to 9 equals 12 to 27. Now, my 4 is my red one, and which over here is the other extreme. 27, right? The outsides are the extremes, and the inside are the means. See how those go together? The reason you want to know all of that is so that way the very first theorem we get introduced to here, which you have to know, memorize, be able to reproduce, and use it to its, like over and over and over again, is Theorem 84. In a proportion, the product of the means equals the back up. In a proportion, the product of the extremes equals the product of the means. In fact, you can even say it in a fun way. The product of the extremes equals the product of the means. Who's with me? You want to chant it together? But you will later in your head. You'll be like, oh, the product of the extremes equals the product of the means. And that'll be the way you end up memorizing it. It's like a little chant. It's a fun way it goes together. It even kind of rhymes. So memorize Theorem 84 that way, and you'll always remember the product of the extremes equals the product of the means. Which will come in really handy with all these problems you're getting ready to do, including using these in its geometry. So we're going to be using proofs. You see the proof there on this page, page 4. It proves Theorem 84. So you're given this, and you're supposed to be able to prove that A times D does in fact equal B times C. Now, when we do this in other situations, we call that what? Cross multiplication? All right, good. So we're not totally lost. Now look at the bottom of the page, just below the proof table. The note section says, note, in the proportion 2 over 3 equals 4 over 6, the extremes are 2 and 6, and the means are 3 and 4. The product of 2 and 6 is 12, the product of 4 and 3 is 12. This is one way to determine if two ratios do in fact form a what? A true proportion. In proportion, they've got to be equal. If any 3 terms of a proportion are known, do you think you could find the 4th one if it was unknown? In a proportion you could, because you know that they're equal. And in an equation, if you've got one unknown in your equation, you can always solve for that one unknown. It's when you've got more than one unknown that it's hard to solve, because you end up with a variable in your answer. So it gives us a nice example at the bottom, which you'll want to pay very close attention to. Solve for x in this proportion, it says. And the proportion we're given is x over 8 equals 3 over 4. So utilizing what we know, x over 8 equals 3 over 4. We've got Step 1. Write it like the product of the means equals the product of the extremes, or product of the extremes equals product of the means. So write it like that. 4 times x equals 3 times 8. So 4x equals, and what's 3 times 8? Anybody, anybody? You can see there it's 24. Divide both sides by 4, and x is 6. So I just solved for my unknown. I know that 6 over 8 equals 3 over 4. Now, you're pretty bright with numbers as it is, so you would probably just be able to look at that and tell. That would be a 6, because double 4 gives me 8, double 3 gives me 6. So you would know it that way too. But if it was much more complex, you'd be able to do it using these steps. That's page 4. Page 5, there's a water tower. And what at first might have been, well, what's the thing below the water tower? Is that a basketball goal?
Mm-hmm.
That's awfully close to the water tower. But hey, you know, is that a Gainesville water tower?
That's what I was thinking earlier.
You see the S-ville, so maybe it's Gainesville. So this would be a proportion in real life. If you have something that you know the height of it, and you can measure the shadow, then you get the length of the shadow of the unknown thing, and you can find its height, because you've created a proportion. The shadow should be the same. The sun is in this one spot, shining, creating two different shadows on two objects at the exact same time.
It's not.
I mean, if you're really slow at doing the work and the sun changes by the time you get over there and measure the other shadow, you might be off a little bit in your numbers. But you'd still be close. It's not like you would get the height of the basketball goal and then go to figure out the water tower and it's like 6 million miles tall. Like, oh, that's a little off. Must have did my proportion wrong. At the bottom of page 5, right underneath number 2, it says write yes or no to indicate whether these ratios can be set to a proportion. So this is page 5 at the bottom. Write yes or no to indicate whether these ratios can be set to a proportion. So all you're going to do is look at it and evaluate, could this be a proportion? Yes or no? And you can see a couple of examples to get you rolling. But number 3, 1 over 3, 4 over 12. Would those, if you put an equals in between them, would those become a proportion? I got one shaking the head, yes. Is that a proportion? Of course it is. What about 1 over 1 and 9 over 9? Yeah, of course that is. 3 over 2 and 2 over 3. Is that a proportion? No. Well, why not? One way you could prove it to me would be by doing this method. If I have a 2 over 3, and I'm trying to figure out is it a proportion to 3 over 2, then I multiply these two and these two. Is 2 times 2 equal to 3 times 3? Clearly not, and so that's not a proportion. What about number 6? Is that a proportion? 6 over 9, 1 over 3?
No.
I mean, at first, it looks like it could be like, oh yeah, oh no. We find that it's not. Number 7, is that a proportion? Number 7, 4 over 9, 24 over 54. That's a proportion. And so you can go through and finish the rest of those. What we want to look at today, your next assignment tomorrow is pages 6 through 10, you got a little bit of something or other you can skip on those pages to save some time, because there is a lot of repeating of work. But let's make sure that these next couple things make sense. First of all, they take the same concept you've just been doing, writing them as a proportion, and going ahead and putting an x value in there for you. Similar to here, only it's not just x by itself. It may be x plus or minus something. You could still solve that using this same method. It wouldn't matter what was in here if this was x plus something, x minus something. You could still solve this as an equation, right? You see that that's what's going to happen on the top of page 6. Does that make sense, what you see there? Any questions about that? Next, we would apply it to a triangle. You see in the drawing there, the blue triangles on page 6. One sits on top of the other. And it's asking you to figure something out. What's it asking you to figure out? You got these triangles that kind of sit on top of each other. Not exactly like that, but pretty close. R is at the top, A is here, S, B, and T. And you're told that RA over AS is equal to RB over RT. Is that right? So it's a proportion because this is the first triangle and this is the second triangle. So R, did I write this correctly?
I think it's BT.
BT. Yeah, that's what you see there, right? I misspelled the R. So this section is proportionate to that section, and so on. Now, if you had actual values, given this, you can plug in what you know and find the unknown. So you actually find an unknown length in these triangles. So that's what you'll be doing there. We get a brand new theorem on page 7, Theorem 85, which doesn't have a lot of words in it. Notice that? It tells you if that original proportion that we learned, A over B equals C over D, then you also know some other things.
Did we do this in algebra?
So you would take those numbers and you could swap them around. And it still works because the product of the extremes equals the product of the means. See how that's continuing to carry itself forward here? Yeah, it is. So you got all kinds of different ways you can write it, but they're still equal. And then you get to prove that. And then here at the bottom of page 7 is something that we're skipping, as well as a good portion of page 8. Because you're supposed to keep going. Because now we get into some really fun shape stuff. Look at page 9 and 10. So those are the last 2 pages you'll be doing. Similar polygons. Do you suppose you'll need to be able to determine if polygons are similar in the future? Of course you will. A lot of highlighting, a lot of things to pay attention to on these 2 pages. It gives you a definition of similar polygons, which you definitely want to pay attention to. Highlight that, put a little mark by it. They are polygons having their corresponding angles congruent and the lengths of their corresponding sides proportional, not congruent. And the symbol we get to use for similar is what? That's fun to draw. So you get to draw that a lot for similar. So if we had one shape A, B, C, D, E is similar to shape, well, they started with Q, but M, N, O, P, Q. 1, 2, 3. I should have counted that out ahead of time. So they would be similar if these were two different shapes. Similar shapes. That's how you would write it. No, we don't know what these are. I didn't draw them. They're made up numbers at this point. But you can look at some of the examples on page 9. And you would see, look at that A, B, C, D rectangle. We see that it's angles. Those check out. They are all congruent because they're all right angles. Easy. And then next to it, we see the shape QRST. That looks like a square. Are those similar polygons? No. Not similar, because the sides aren't proportional. So read over that, and then you get to use our marking system. So if you have one shape and then some other shape, if these are the same, something like that, you get to use those hash marks to indicate things that are congruent sides, and that might help you be able to move forward. Hey, is this proportional to that? You will get to find out. But your reason has to include both parts. In order for you to say, these are similar polygons, you have to have both parts of that definition. The corresponding angles are congruent, check. The lengths of their corresponding sides are proportional, check. If not, they are not similar polygons. Got it? That's the only way you're going to be able to say they are or are not. So you get to practice those on page 9 and the top of page 10. You get to find some unknown lengths given similar polygons. And then there's a note section down there in the box. You'll definitely want to pay attention to that. And we have time to read it together really quick.
I'm sad I didn't waste any more time in class. Doing so much work.
You what?
Sad I didn't waste time in class doing too much
This is
work.
what usually happens when you're not here.
I've been quiet this class. Just see how much we
The note box does say on page 10, setting up proportions of similar polygons is not difficult. Yay!
find that
That's comforting. I thought it was going to be hard, and now I read that they're comforting me with their words. Like the Bible says, comfort one another with these words. So they're comforting us with these words that they are not difficult. So now you can take that load off. Oh, then there's this however after it. So that kind of makes me wonder, there might be a caveat to this. If proportions are set up wrong, you cannot get the correct answer. Don't set up your proportion wrong. Easy. As indicated in Theorem 85, there are 4 ways to correctly set up any one proportion and get the same answer. You got 4 ways. I mean, how are you going to get it wrong? You're not going to get it wrong. I mean, you might. Because if you do it wrong, it won't work out. But look back at Theorem 85 and see all the different ways you can arrange your proportions. Using a proportion to solve for an unknown segment is based on knowing 3 of the 4 proportional parts. We studied that earlier when we had an x here and we knew the other 3 numbers. You can solve for that, one unknown, and get an answer. Now here is where it picks up some really important stuff. So you set up the proper ratio, multiply the extremes, then multiply the means, and solve for the unknown. Now, here's the thing to pay attention to when you're scoring, of course. The solution key will only work with the proportion one way. If you set up the problem according to the following guidelines, your method should match the method in the solution key. However, setting up the problem differently may not mean your answer is wrong. It just won't match what's in the score key because you set your proportions up differently. So you got these three things you really got to pay attention to. Number one, the proportion will usually be in the form of the values of the large polygon over the values of the small polygon. Number two, the first ratio of the proportion will consist of the known values between corresponding sides of the two similar polygons. You may need to reread that, but that will make sense. And then third, the second ratio of the proportion will consist of the other two corresponding sides necessary to solve for the unknown, last word, value. So read over those. Don't just expect to read it once and like, oh yeah, I got all three of those things. Boom, boom, boom. Check 1, 2, 3. They will become very obvious. You will see how simple this is. And then you'll refer back to that first sentence. Not difficult. I mean, this could be true of so many things in math. It's not difficult if you just set the problem up correctly and do the work right. Oh, thanks a lot. But isn't that always true? Think about word problems. If you set up your word problem correctly, not difficult. If you don't get it set up or you get it set up wrong, the problem will become very difficult and it won't work. So just like this. So pay attention to how you set up your proportions. Just follow the same process each time. Get in the habit of doing it the same way, in other words. And then if you happen to get an answer that doesn't match the score key, just check it with me or write it the other way and see if that comes out correctly. You'll know if you got your proportion set up right. But they're giving you this, hey, if you do it this way, then it will match our answers, but you can do it your way and maybe get a different answer. But it might still be right. Challenge accepted? So now we got through today, and we covered what you're going to need to know to finish up tomorrow, and then we come back to class again next time.